Now, Poisson's ratio, not Poisson's ratio, Poisson. Think of reading it in a French accent. This is the ratio of elongation and compression in the direction of the stress and perpendicular to it. So, elongation, special formula to calculate elongation, length final minus length initial divided by length initial, or delta L over L initial, or L naught. When you have the symbol with the little O instead of an I, for example, that little O is pronounced naught, and it means initial condition. I know most of you are probably familiar with that, but I want to say it just in case. So E, elongation, lowercase e, different than the capital E we saw before. Length final minus length initial divided by length initial. We can calculate this for any of the three axes, but we don't call them X, Y, and Z. We call them 1, 2, and 3. This tells us largest, smallest, and medium. Now, Poisson's ratio specifically only deals with largest and smallest. So the ratio of elongation in the largest stress direction and smallest stress direction. Mu, think of the Pokemon, mu, the almost like backwards lowercase letter u, is negative E3 divided by E1. So elongation in the small direction, smallest stress direction, divided by elongation in the largest stress direction. Now think about your Play-Doh. If you have a piece of Play-Doh on the desk and you push down on it, the largest stress is in that vertical axis. You're pushing down on it. In that direction, it's getting shorter. So elongation is actually negative. You know, if it was 2 inches tall, that was your length initial. After you squish it, it's a ½ inch. That's your length final. You have 0.5 minus 2 divided by 2. And that's E1, because that's in the direction of the greatest stress. E3 is one of the sides. You know, in this case, there's no difference between, you know, the X or the Y direction, assuming Z is the vertical, because both X and Y directions, the only stress is atmospheric pressure. So you pick one of them as your E3, and you measure, hey, you know what, I started with a 2-inch cube. After I compressed it, it's like 4 inches wide. So you calculate your E3 using length initial 2, length final is 4, and calculate your E3. Mu will always be between 0 and 0.5. If you get anything else, you know you did something wrong. Maybe you forgot your negative sign, maybe you calculated when your E's incorrectly, maybe you used one of the wrong components, like you used E2 instead of E3. If it's not between 0 and 0.5, a positive value, recalculate your Poisson's ratio. Viscosity is resistance to flow. So viscous behavior is flow that doesn't return after you remove the stress, And viscosity is the resistance to flow. So water has pretty low viscosity. You pour water on the disc, it goes all over the place. Honey or molasses or toothpaste have reasonably high viscosities. You pour them on the desk and they slowly spread out and go all over the place, far slower than the water. Play-Doh or silly putty has much higher viscosity. You set that on the table and it takes a very long time to spread out. The Play-Doh might even dry out and become rigid before it spreads out fully. The silly putty, if you come back the next day or maybe that night, will be spread out reasonably thin. Viscous behavior is irreversible. Unless you apply different stresses in different directions, it will never return to anything even resembling its original condition. And even with other stresses, it won't return to precisely its original condition. Viscous behavior is irreversible. So sigma stress equals this special N viscosity times E with a little dot over it, which is the strain rate, how fast it is strained, how much deformation per second. If you look at table 5.5 on page 97 in your book, you can see some values and information about viscosity. Now, the special cases. Viscoelastic and elastico-viscous. They're not the same. That's why they have different words for them. So viscoelastic behavior and elastico-viscous behavior. Viscoelastic is deformation is reversible, but the recovery is delayed. This is like a memory foam mattress. You press on that memory foam, it deforms. You stop pressing on it, you see a cool imprint. If you come back in an hour, the imprint's all gone. It looks like nothing happened. It recovered from that deformation, but very slowly. It was delayed. This is a lot like the crust of the earth, delayed for thousands of years. It responds viscoelastically. Geologically speaking, 1,000 or 10,000 years is fairly instantaneous, so we can talk about it as being elastic behavior. In a human lifespan time frame, it's definitely viscoelastic. Now, the other one, elastico-viscous, is when the material behaves as an elastic substance initially, but if more force is applied, it'll behave in a viscous manner. So this is like silly putty. If you have some silly putty and you push just a little bit and release, it kind of springs back. It behaved elastically. If you push a bunch, then you go past that elastic portion and it behaves viscously. Or let's see, another example. If you have a spring on, or a bungee cord on a heavy box, if you pull on that bungee cord or on that spring a little bit, it deforms, and you let go, and it goes back to the way it started out. It's the same shape and in the same position. Because remember, moving something, translating it, is deformation. So that's important. Because if you pull really hard on that spring or on that bungee cord, your heavy box will actually move. Therefore, your spring or your bungee cord moves. So even though with a little bit of stress, it behaved completely elastically, with a lot of stress, it's now viscous behavior. It won't return to normal because it's in a new place. Even if its shape goes back, there was permanent deformation. It moved.